Welcome back to The Explainer. Today, we're diving into the extreme, high-stakes world of deep earth drilling. You know, people often picture drilling a well as just poking a really deep hole in the ground. But the reality? It is so much more violent and way more complex than that. Imagine pushing 2 miles down into the Earth's crust. You're dealing with shifting rock, unbelievable underground pressures, and highly volatile trapped gases. To actually survive down there, a well needs a permanent, basically indestructible architecture. So today, we're going to break down the absolute most critical, expensive, and permanent physical structure in any oil or gas well. We're talking about casing, the well's skeleton.
There's this fantastic, really evocative quote in the industry. A freshly drilled hole is not a hole. It's a wound in the ground. And honestly, that is the fundamental truth you've got to understand about the Earth. It does not want to be open. The very second that drill bit grinds through the rock, that wound starts trying to heal itself. It tries to close. The walls immediately start to slough and cave in. Water from different zones bleeds into the open space. Trapped, highly pressurized gas starts clawing its way up toward the surface. If you just left a well as raw rock, it would literally destroy itself in a matter of days, just bearing millions of dollars of equipment in a collapsed tomb of rubble.
And that brings us right to the raw hole problem, which happens to be the biggest single material cost in this whole process.
So, how do we solve it? With a telescoping anatomy made of 5 strings of casing. See, to stop the Earth from caving in and closing that raw hole, engineers have to step in and forcefully hold it open. We have to line the entire depth of the well with high-grade steel pipe and then permanently cement it into place. This is a forever fix, which is why it's the biggest material expense on the ledger. But casing isn't just dropping one giant, long straw into the ground. It's a highly engineered, multi-layered system that does 3 crucial things. It stops the walls from caving, it prevents different fluid formations from migrating and mixing together, and it helps the crew maintain total well control at the surface. And, as you'll see, it's built in very specific phases as the drill bit goes deeper.
The way they actually assemble this skeleton is pretty fascinating. There are basically 5 primary strings of casing. We kick things off with the conductor pipe at the very top. Then comes the surface casing, followed by the intermediate casing, then the liner, and finally the production casing all the way at the bottom. The really important thing to notice here is the physical geometry. Each new string of casing is run inside the previous one. That means the well physically telescopes downward. It's at its absolute widest diameter at the surface, and it just gets progressively narrower and narrower the deeper you go. And every single one of these layers has a very specific job to do. That conductor pipe, it's short, it's wide, and it simply holds back the loose topsoil and gravel at the surface so the rig doesn't just sink into its own hole. But then you have the surface casing, which is absolutely vital. Its main job is to isolate and protect shallow freshwater aquifers. In fact, running and cementing surface casing is a strict legal requirement almost everywhere on Earth to make sure drinking water is never contaminated. Below that, the intermediate casing acts like a heavy-duty shield, sealing off any unstable or extremely high-pressure rock layers that might cause a blowout. And finally, at the very bottom is the production casing. This is the only string that actually gets perforated, shot with explosive charges, so that the oil and gas can finally flow into the wellbore.
So this leads us to the pressure window. Why do we need 5 strings instead of just 1? Well, this is where we run into a brilliant, invisible engineering conflict that literally dictates how every deep well on the planet is designed.
Here's how it works. As you drill, you're constantly pumping heavy drilling mud down into the hole. Now, this mud has to be heavy enough to hold back the immense natural outward pressure of the underground formations. If the mud is too light, the well kicks and blows out. But on the flip side, if the mud is too heavy, the sheer hydrostatic weight of it acts like a giant hydraulic wedge. It'll physically fracture the rock walls and all your mud will just drain away into the earth. The tiny gap between those two extremes, mud heavy enough to hold the well but light enough not to break the rock, is what we call the pressure window. And the kicker is, as you drill deeper and deeper, that window violently narrows. Which means each casing string represents the exact depth where that pressure window slammed shut. Casing points aren't just arbitrary depths picked out of a hat. They are set exactly where the engineers literally ran out of safe room to drill. When the formation pressure and the fracture pressure converge, you can't go even 1 foot deeper safely. You are forced to stop, run steel casing down, cement it in to seal off everything above, and then start a brand new, slightly wider, pressure window with fresh rock below.
Now, let's talk about the extreme physics of surviving the 3 loads. Because once the engineers figure out where the casing needs to go, they have to make sure the steel actually survives once it's locked into the earth. It's subjected to a truly terrifying triad of physical forces.
It boils down to 3 primary failure modes.
First, you have burst. This is extreme pressure from inside the wellbore trying to inflate and split the steel pipe open like a balloon. Second is collapse. That's the exact opposite. Massive, crushing pressure from the rock and fluids on the outside trying to flatten the pipe like a stepped-on soda can. And third is tension. This is literally just the string's own hanging weight. Think about it. A casing string can be miles long. The steel at the surface has to hold up the weight of all the steel below it, which can easily be hundreds of thousands of pounds. A pipe designed to resist bursting might just snap under tension. That's exactly why casing isn't something you just pick out of a catalog. It requires a rigorous, per-well mathematical calculation to ensure that specific steel can survive all three of these loads simultaneously.
And we really have to highlight a massive operational trap right here, surge pressure. When a rig crew starts lowering this massive, wide steel string into the hole, the pipe acts exactly like a giant plunger in a syringe. If they run that casing in too fast, it creates a massive hydraulic shock wave, a surge of pressure right ahead of it. This surge can instantly fracture the rock formation below. Boom! Suddenly, you lose your drilling fluid, you lose well control, and you've just created an unbelievably expensive disaster while doing a task that felt totally routine. Running casing is a strictly controlled parameter. You never, ever just drop it in as fast as you can.
Now, I know what some of you are probably thinking right now. It's a great question. If all this telescoping and calculating is so complicated, why not just run one incredibly thick, massively strong string of casing all the way from the surface straight down to the bottom?
Well, here is the reality check. You physically cannot drill a 30-inch wide hole down to 15,000 feet. There isn't a rig on Earth that has the rotational torque or the hoisting capacity to manage a drill string that massive at that kind of depth. Plus, because of that narrowing pressure window we just talked about, the physical demands of the well change drastically as you go down. A single uniform pipe would be ridiculously expensively over-designed for the top of the well and completely fatally under-designed for the bottom. Telescoping isn't just some compromise, it's literally the only physical geometry that actually lets us reach these deep targets.
Which brings us to the well's composite skeleton, a truly permanent structure. We've gone over the intense physics and those nested strings, but we really need to grasp the permanence of what's being built here. See, a drilling rig is huge, it's noisy, it's highly visible, but it's entirely temporary. It shows up, drills the hole, and drives away. But the casing? That steel skeleton stays in the earth for 30, 40, sometimes even 60 years. Long after the rig is packed up and left, that casing is going to sit there, carrying the immense weight of the wellhead at the surface and enduring the punishing pressures of the deep earth for decades on end.
And here is the ultimate payoff. A composite skeleton is the combination of steel casing, cement, and the surrounding rock formation acting as a single unified structure. Here's the crazy secret. The steel casing pipe actually isn't strong enough to survive down there on its own. It only gains its true strength when liquid cement is pumped all the way down the inside, pushed up the outside of the pipe, and allowed to harden, chemically bonding the steel directly to the rock. It's this composite structure, the steel, the cement, and the rock acting as one, that makes it a structural marvel. And it's exactly why a bad cement job isn't just a minor cosmetic issue. It is a catastrophic, well-ending structural failure. Which leaves us with a truly fascinating, high-stakes question to ponder. If the structural integrity and the safety of a multi-million-dollar well relies entirely on a layer of cement that is buried thousands of feet underground and completely hidden behind an impenetrable wall of steel, how on earth do you guarantee that bond holds? How do you test something you can't even see? It's a massive challenge, and it's exactly what we're going to break down in our next explainer when we dive into wellheads and cement evaluation. Thanks for joining me on this one, and I'll see you next time.